I want to look at an example here where we're using rectangles to approximate areas. This is actually an example we've done already. So you guys remember this data? This is from like the first day of school. I gave you a little activity to do, kind of an introduction to a couple of calculus topics, and this was one of them. And so a lot of you came up with what is the rectangular approximation method on your own. So let's say that we wanted to use left rectangles to approximate the distance that we travel in our car given this data. So at different times where t is measured in hours, we know how fast the car is going. We want to know how far the car went during this time period. Now, the first thing we need to understand is with this data, and we're going to see a lot of problems like this where we're given data. Anytime you collect data like this on something that's continuous, but we don't have continuous data, we're not going to be able to get a complete picture of it. We don't know exactly what happened for the 12 minutes between 2 o'clock and 2:12, and the 12 minutes between 2:12 and 2:24. So we don't know what's going on in between, but we can kind of get a big picture guess as to how far we went. So let's say we want to use left rectangles. What does that mean we're going to do? The assumption with the left rectangles is that the value of the function, and in this case the function we're looking at is the speed of our car. The assumption is the value of the function over this period that's 2/10 of an hour long is the same as it was at the beginning of that interval. So the assumption is we're driving 70 miles an hour for 12 minutes. Then suddenly we drop to 45 miles an hour for 12 minutes. Then suddenly we're driving 30 miles an hour for 12 minutes, and so on. Obviously, that's not even physically possible. You can't decelerate from 70 to 45 in an instant. It takes some time to do that because the car has mass. You guys that are taking physics probably know that, hopefully. But in case you didn't, you can't do that. But that's the assumption. We're going to work under that. And so what ends up happening is that this speed here at the end, it's useless. We're not going to use it. With that assumption, we're assuming that we're driving 15 miles an hour for these 2/10 of an hour. So it doesn't matter how fast we're going at the end of this interval. So if we were going to do a left rectangular approximation method to find the distance traveled, we might say d is approximately equal to the LRAM. You always want to make sure that you indicate which one you're using. And so using the left rectangles, we're going to take, as Ben said, our speed, which was 70, times the time that we traveled for that speed, and the assumption is that we traveled it for those 2/10 of an hour. So it's going to be 70 times 2/10 of an hour. That's going to tell us how far we traveled during those first 12 minutes. Then for the next 12 minutes, we take our speed at the beginning of that interval. So we're going to add on. I'm going to stack this just so it looks a little bit better because I know I'm going to run out of room. So we're going to take 45 times 0.2. And then we're going to add on what? 30 times 0.2. And you guys may notice here, we talked about this yesterday, since we have 0.2 in every one of these terms, what could we do to make the calculation just a little bit easier? Factor that out. So what we can do here is we can add all of these up. 70 plus 45 plus 30 plus 10 plus 15, and then take that sum and multiply it by 0.2 and get our approximation, which is going to be what? So we get 34. Now, one other thing I want to look at here, and this is really, really useful when we're doing calculus, is the units. Don't just say this is the number 70 by itself, but this is 70 miles per hour, right? And this is 2/10 of an hour. So when we multiply miles per hour times hours, what are we going to get? We get miles, because those hours cancel each other out. So when we do that computation for each one of these are all miles that are being added together. So our answer is going to be miles. So this isn't foolproof. The units don't always tell you exactly what it means. Sometimes it can be a little deceiving, but for the most part, they're pretty good at telling you what these areas tell you. And don't forget, these are areas of rectangles, right? we were to graph this, if we were to plot these points and graph this, we would be finding the areas of rectangles in that coordinate plane. So these miles units are telling us that we're finding a distance of some sort. In this case, it's the distance that the car traveled, or at least an approximation of it. I'm not going to go through and do the same thing for the RRAM, but if we were going to do the right rectangular approximation method, what would we do differently?
Let's start at 45 and go to the 70.
Yeah, we would start with the 45. So the assumption with the right rectangles is that the value of the function is equal to the value of the function at the right edge of the interval. And so we would assume that over this first interval from 2 o'clock to 2:12, we're driving 45 miles the entire time. Okay, so it doesn't matter what we are actually driving at the beginning of that interval. We're going to assume that it's 45 the whole way. So we're using the right endpoint to find the value. It actually turns out that since the right endpoint of the last interval is the same as the left endpoint of the first interval, we end up getting the same value here, right? Okay, so either way, whether you're doing LRAM or RRAM, you get 34 miles. The only difference would be that this 70 times 2/10 would be at the end of your calculation instead of at the beginning. So one thing is that the intervals here that we have, those are regular intervals. Okay, they're equally spaced. They're all 12 minutes long or 2/10 of an hour long. That's not always going to be the case. So if we have like an interval that's 2 minutes and then another one that's 10 minutes and another one that's half an hour and then another one that's 15 minutes, we wouldn't be able to factor out that delta x. This is the delta x here, actually delta t in this problem. So we wouldn't be able to factor that out. We'd have to do each one of those computations separately. So be aware of that. If you have a problem where the intervals are not equally spaced, then you're going to have to do each calculation by itself, and just be careful about that. That's kind of inconvenient though, because if it's not equally spaced, then it makes you do a lot more calculations. It makes you do all of these products here first and then add them together. So if we have an option, we like to have our intervals equally spaced because it just makes things a lot easier for us. Another thing I want to point out about this is if we wanted to use midpoint approximation method, would we be able to do that with the data we have here? No. Why not? So we wouldn't be able to do the midpoint here because let's say we wanted the midpoint of this interval from 2 o'clock to 2 2/10. We don't know what's happening at 2.1, at t equals 2.1. And that's the value we would use if we wanted to use the midpoint. Now what we could do is we could do the midpoint approximation method from 2 o'clock to 2:48 and use two intervals and say, okay, we're driving 45 miles an hour from 2 o'clock to 2:24, and then we're driving 10 miles an hour from 2:24 to 2:48. So I could use this point here as a midpoint between 2 and 2.4. And I could use this point here as a midpoint between 2.4 and 2.8. The problem with that is we're losing a lot of data that could be helpful for us in making a more accurate approximation. And the other thing is, if we really wanted to do that, we would lose the last 12 minutes of our data also. It would be useless. Okay? Now, we talked about this before, but the rectangular approximation method doesn't really seem to be the best because we're assuming that we're driving 70 miles an hour this entire interval, but we can see clearly that we're not driving 70 at the end. So what kind of adjustment did we make when we did that?
Would you just go to trapezoid?
So geometrically, what we would end up doing is using a trapezoid, and essentially what that does is it averages the beginning speed and the ending speed in this case. So if we average 70 and 45, we're probably going to be getting a more accurate speed or more appropriate speed for the length of the interval rather than just using the beginning or the end speed. Okay, so we could take the average, and by doing that, we're finding the area of a trapezoid. Okay, this is actually really important. Should have been easier for me to think of. When we're doing the area problem, you guys are going to start noticing that we're almost always going to have a rate. Okay, so speed is a rate of change. Now remember, when we did the tangent line problem, we were finding rates of change, right? Well, now what we're dealing with is a function that is a rate of change, and we're almost going backwards. So before we had a function and we found the rate of change, now we're going to have the rate of change and we want to know what the function was. So what I mean by that is we have the rate of change of the position of the car right now, and what we end up trying to find is the change in the position of the car. So we want to know how far the car traveled, which would be the change in position. So when we're doing the area problem, our units for along the horizontal axis are almost always along the vertical axis are almost always going to be a rate of change. So it's going to be miles per hour or gallons per minute, or usually you're going to deal with time. They don't necessarily have to be time, but we're going to be dealing with rates. And that's important to remember, because when we multiply a rate times a unit, a time unit in this case, those units are going to cancel each other out.